Welcome to this lecture on the hypothalamo-hypophyseal-gonadal axis, often just called the HPG axis. If you have ever wondered how the human body knows exactly when to initiate puberty, or how it maintains fertility day after day without us even thinking about it, you are in the right place. This axis is the master control system of human reproduction. By the end of this video, you will understand not just the biology of these organs, but the elegant mathematical balance that keeps our hormones perfectly regulated. To understand how this complex system works, let us start with a simple analogy. Imagine a smart heating system in a modern house. The thermostat on the wall senses the room's temperature and sends a signal to the furnace to produce heat. When it gets too hot, the thermostat turns the furnace off. Our reproductive system works exactly like this. The brain acts as the master thermostat, constantly monitoring the levels of reproductive hormones circulating in your blood. Instead of electrical wires, it uses chemical messengers to send instructions down to the reproductive organs, which act like the furnace. This continuous, self-regulating loop ensures perfect balance. Now that we understand the thermostat analogy, let us look at the actual biological hardware. The HPG axis consists of three main anatomical components. First, we have the hypothalamus, a small but crucial region in the brain that acts as the initiator. Second is the hypophysis, which is the scientific name for the pituitary gland, located just below the brain. Finally, we have the gonads, which are the testes in males and the ovaries in females. These three distinct regions communicate across the body to regulate reproduction and development. Let us trace the exact chain of command between these organs. The hypothalamus starts the process by secreting gonadotropin-releasing hormone, or GnRH, in rhythmic pulses. This hormone travels a very short distance to the anterior pituitary gland. In response, the pituitary releases two more hormones, luteinizing hormone, or LH, and follicle-stimulating hormone, or FSH. These pituitary hormones then travel through the general bloodstream all the way down to the gonads. Once there, they trigger the maturation of sperm or eggs and stimulate the production of sex steroids like testosterone, estrogen, and progesterone. This brings us to the most critical part of the system, how it turns itself off. Once the gonads produce sex steroids like testosterone or estrogen, these steroids do not just affect the body, they travel back up to the brain. When the hypothalamus and pituitary detect high levels of these steroids, they decrease their production of GnRH, LH, and FSH. This is a classic negative feedback loop. Just like the thermostat turning off the furnace when the house is warm, this inhibitory feedback prevents hormone levels from rising too high, keeping everything in perfect biological equilibrium. Let us consolidate what we have learned by looking at this schematic diagram. At the top, you see the hypothalamus sending positive stimulatory signals, marked with a plus sign, via GnRH to the anterior pituitary. The pituitary then sends LH and FSH down to the gonads, again as positive stimulation. The gonads produce sex steroids. Now, follow the red line looping back up. This represents the negative feedback, marked with a minus sign. The sex steroids inhibit both the pituitary and the hypothalamus. This visual perfectly captures the delicate balance of stimulating signals and inhibitory feedback that defines the HPG axis. Before we dive into the mathematics of this system, we must understand why the HPG axis matters in real life. This axis is the absolute foundation of reproductive biology. Without it, humans would not undergo puberty or be able to reproduce. In modern medicine, doctors actively manipulate this exact chain of command. For example, daily birth control pills provide steady levels of synthetic estrogen and progesterone. This tricks the brain into thinking the gonads are already working hard, which activates the negative feedback loop, shuts down the HPG axis, and prevents ovulation. We also target this axis to treat infertility and manage hormone-dependent conditions like prostate cancer. Now that we understand the biology, let us look at how we can represent this balance mathematically. To truly understand how hormone levels are maintained, we use a basic rate equation. The formula is dC by dt equals P minus K times C. Conceptually, this means the change in hormone levels depends on how much new hormone is pumped in minus how much is filtered out. P is the production rate, driven by the brain's signals. The variable K is the clearance rate constant, representing how quickly the liver and kidneys remove the hormone. C is the current concentration. If production P increases, the concentration C will rise until the clearance catches up. Let us apply this formula to a concrete example. A male patient produces testosterone at a constant rate of 6 milligrams per day. His clearance rate constant is 0.1 per day, and his volume of distribution is 10 liters. We want to find his steady-state blood concentration. First, at a steady state, the hormone level is not changing, so the rate of change is exactly 0. We set our equation to 0 and use total mass M to find out how much hormone is in the body. Rearranging gives us M equals P over K. Plugging in our numbers, 6 divided by 0.1 gives a total mass of 60 milligrams. Finally, we divide this mass by the 10-liter blood volume. The final answer is 6 milligrams per liter. This is his stable, healthy testosterone concentration. Having just used the steady-state formula, let us take a moment to formally derive it, so you understand exactly where it comes from. We start with our continuous rate equation. The mathematical definition of a steady state in biology is that the amount of hormone entering the blood perfectly equals the amount leaving it. Therefore, the rate of change is 0. We substitute concentration with total mass M to look at the whole body. This gives us 0 equals P minus K times M. By moving the clearance term to the other side, we see that clearance equals production. Dividing by K isolates M. This simple derivation proves a profound biological truth. The steady-state mass is directly proportional to production and inversely proportional to how fast the body clears it. Our previous formula assumed hormone production was a smooth, continuous stream. However, biological reality is more complex. The hypothalamus actually releases GnRH in discrete, rhythmic pulses, not a steady flow. This pulsatile secretion is absolutely crucial. If GnRH were released continuously, the pituitary receptors would actually shut down and stop working. Each pulse of GnRH causes the pituitary to release a sudden burst of LH into the bloodstream. To fully understand the HPG axis, we need a way to bridge the gap between these discrete biological pulses and the continuous mathematical averages we just learned about. To handle these pulses mathematically, we define a new formula for the average production rate. The formula is P equals delta C times F. Conceptually, this translates the biological reality of rhythmic hormone bursts into a continuous mathematical rate that we can use in our steady-state equations. Delta C represents the concentration jump in the blood caused by a single pulse. The variable f represents the frequency, or the number of pulses per hour. In plain English, this means if the individual pulses are larger, or if the pulses happen more frequently, the overall average production of the hormone goes up. Let us see how the brain calculates the required pulse frequency. Suppose each GnRH pulse increases blood LH concentration by 2 international units per liter. The clearance rate is 0.5 per hour, and the body needs to maintain an average steady-state LH concentration of 12. How many pulses per hour are needed? We use our pulsatile steady-state relation, where production equals clearance. Rearranging to solve for frequency f, we get K times C average divided by delta C. Plugging in our numbers, we multiply 0.5 by 12 to get 6, and then divide by the pulse size of 2. The final answer is 3 pulses per hour. Physically, this means the hypothalamus must fire a signal exactly every 20 minutes to keep the system adequately stimulated. Now that we have calculated the required frequency, let us quickly prove where that specific arrangement came from. We start with the fundamental steady-state balance. Total hormone input must equal total hormone output. The output is the clearance rate, K, times the average concentration. For the input, we substitute our pulsatile production definition, delta C times F. This gives us delta C times F equals K times C average. To isolate the frequency F, we simply divide both sides by the amount released per pulse, delta C. This derivation proves that the required pulse frequency is directly proportional to the target concentration and inversely proportional to the size of each individual pulse. We have covered a lot of ground today, so let us summarize the key takeaways. First, the hypothalamo-Hypophyseal-Gonadal axis is the master control system for human reproduction, operating through a delicate balance of stimulating signals and inhibitory negative feedback. Second, we learned that hormone levels in the blood are mathematically maintained by balancing the rate of production against the rate of clearance. Finally, we saw how the brain uses discrete, rhythmic pulses of GnRH to drive this continuous biological system. Understanding this axis provides the exact mechanisms we use in modern medicine to treat infertility and develop contraceptives. You now have a solid foundation in reproductive biology.